Hello guys, thanks for clicking on this video. So today we are going to start with our first lecture on thermodynamics, the revision of thermodynamics. It will be a series on thermodynamics, and thermodynamics is the love of every engineer. Everyone love thermodynamics. Like, I don't know about other, but yeah, I love thermodynamics. It was my first girlfriend and my friend's girlfriend also. So yeah, thanks for clicking on this video. And this video will be a shortest video. Like, I'll explain every single point, I will touch every and each point, but I will not explain the things in a vast manner. So yeah, let's start. So our first topic is, our first term is open system. Open system are the system in which we control the volume, but we don't control the energy and the mass. So we allow to transfer the mass from one point to another, we allow energy to transfer from one point to another point, but we don't allow the volume. We maintain the volume constant. So this is our first system, open system. So the example of open system is aeroplane and turbine. These are the most important examples of open system. Sorry. So 90% of practical applications are depend upon open system. This is the open system. Now this is how I will cover the terms. Like, next is closed system. Closed system is a very basic term. Like, in closed system we control the mass, but we don't control the energy. Like, we allow to transfer energy from one point to another point, but we control the mass. We don't allow mass to be transferred from one point to another point. The basic example of closed system is pressure cooker without valve and the IC engine without valves. And why these are closed system, like pressure cooker and ice engine, why these two are closed system? Comment down why these are closed system. I want to know, do you know or not? If you don't, I will explain in my next lecture. So next term is in intensive property. Intensive properties are those properties whose value of entire system is not equal to the sum of their value for individual part. Like, I can't add or subtract the property. Like, this is a basic. Let me explain this in a vast manner. So suppose I have a I have a system. Like, suppose this is my room and this is my system. So if the temperature of that left corner is 15 degrees Celsius and the extreme right corner temperature is also 15 degrees Celsius, and if I added these two temperature, it will become 30 degrees Celsius, and this will not be equal to the individual part of my system. Like, it will not be equal. Like, 30 degree will never be equal to 15 degrees Celsius. So another example, if you don't get this, another example of this uh, intensive property, which will be, if I have a jar and I put it some water at 4 degrees Celsius into the jar. I put I put some water into the jar which is at 4 degrees Celsius, and the density of water at 4 degrees Celsius is 1000 kg per meter cube. Again, I put it some more water which is at 4 degrees Celsius. I put it the water again into that jar. Does the density of that water will change? I added the water into water, like, I added more water into water. Will the density of water change? No, no, sir. The density will remain constant. So I added the mass, but the change in density is 0. That's why if I added mass, the change in property is 0. That's why intensive property does not depend upon mass. These are independent upon mass. That's why all specific properties are intensive properties. Like extensive properties are depend upon mass. I will explain it later. Extensive properties depend upon mass, and when I divided them by mass, they will not depend on mass again. So that's why all specific properties are independent of mass, and those properties which are independent of mass are intensive properties. The very basic example of intensive properties are pressure, temperature, viscosity, density, and surface tension and concentration. Concentration is a term of chemistry. I will consider it into thermodynamics, because thermodynamics is a bridge of chemistry and physics. So the example of intensive properties are pressure, temperature, viscosity, density, surface tension, boiling and melting temperature, magnetic permeability, thermoconductivity, and concentration. So now the next term is extensive properties. Extensive properties are those properties whose value of entire system is equal to the sum of their value for individual part. Now I will explain it again, and it will be easy if you get the basic idea of intensive property. So it will be easy to get the idea of intensive property. suppose i have a jar suppose I have a jar, and I put some energy into it, like tiny energy. I put some energy into the jar. Can I add some more energy into it? Suppose I have a ball, and I put that ball from a 10-meter height. So the potential energy will be equal to P, Z, and Z. Yeah. So I can, this is the potential energy. So I can increase the potential energy. Yes, if I increase the height, the potential energy will also increase. So intensive properties are those properties entire system value will be whose entire system value is equal to the sum of their value for individual parts. So are all energies can be added or can be subtracted. So yeah, all energies are intensive properties which are not depend upon mass. Which are depend upon mass. Which are depend upon mass. So examples of intensive properties are amount of substance, entropy, energy, gives energy, heat capacity, and most important example is mass and volume and Helmholtz energy. So next term is our basic equation of ideal gas equation is PV is equal to nR bar T. nR bar T. So this is the raw equation. This is converted into PV is equal to MRT. How it is converted? So R bar is a universal gas constant which will be equal to 8.314 kilojoule per kilomole Kelvin. If I convert the value of n, which will be equal to mass divided by molecular weight, so I put the value of n is equal to mass into molecular weight. So R bar divided by molecular weight becomes characteristic gas constant, and mass take place on the place of n. So characteristic gas constant depend upon molecular weight, so it changes. For A it is 287.058 joule per kg Kelvin, or if I converted joule into kilojoule, it will become 0.287 kilojoule per kg Kelvin. And I can get the value of R bar from Avogadro law multiplies by Boltzmann constant. So Avogadro number is 6.023 into 10 to the power 23, and Boltzmann constant is 1.38 into 10 to the power minus 23. If I multiply these two values, I will get 8.314 kilojoule per kilomole Kelvin. So this is my basic equation of ideal gas. Now these are two values which I have to remember. So specific heat at constant pressure is and specific heat at constant volume depends upon temperature for an ideal gas. So specific heat at constant pressure value is 1.005 kilojoule per kg Kelvin, and specific heat at constant volumes value is 0.78 kilojoule per kg Kelvin for ideal gas. And for real gas, Cp and Cv doesn't divide upon temperature, does not depend upon temperature. So there is a very basic question: how I can get ideal gas? Like, there is no ideal gas exist in our real life. There is only real gases. So how I can convert a real gas into an ideal gas? So this is my answer for those questions. Like, at higher temperature and low pressure, a real gas behaves as an ideal gas. This is the answer of that question. So now next term is from same topic, like PV is equal to nRT. Here we go. Velocity root mean square, which will be equal to under root of 3 r by t divided by molecular weight, or it will be equal to under root of u square plus v square plus w square. And velocity root mean square depends upon under root of temperature under root of temperature and kinetic energy. And kinetic energy depends upon temperature. And kinetic energy for n mole of gas will be equal to, kinetic energy will be equal to 3 by 2 n r bar t. And two more equations: pressure of gas will be equal to 1 by 3 density into velocity root mean square ka square. And kinetic energy will be equal to half mv square, and v is velocity root mean square. Next, these are some basic statements which give us the processes like isothermal process, isobaric process, and isochoric process. These are the statements which give us those processes. So Boyle's law says at constant temperature, pressure will be inversely proportional to the volume. And another statement is Charles law. It says at constant pressure, volume is directly proportional to temperature. And another statement of this law is all perfect gases changes in volume by 1 divided by 273 part of its original volume at 0 degree Celsius for every 1 degree Celsius change in temperature at constant pressure. So at minus 273 degree Celsius or 0 Kelvin, the volume of the gas will become 0, which is impossible by third law of thermodynamics. We will come to third law of thermodynamics in upcoming lectures. So Boyle's law give us isothermal process, Charles law give us isobaric or isopastic process, and Gay-Lussac law give us isochoric or isometric process. Gay-Lussac law is says at constant volume, pressure is directly proportional to the temperature. Avogadro's law says equal volume of all gases at the same temperature and pressure contains equal number of molecules. So volume is directly proportional to number of molecules at temperature and pressure when temperature and pressure are constant. And two more statements, like Joule's law says change in specific internal energy will be equal to mass into specific heat into change in temperature. And Dalton's law says total pressure of a container will be equal to the partial pressures like P1 and P2 and P3 and so on. So this is the first lecture of thermodynamics. Thanks for watching, and I will make a continuity on this. And in next lecture we will cover the basic terms like the PV graph, work done, polytropic and adiabatic processes, and work done and heat transfer. And after that we will cover zeroth law of thermodynamics, and then after this we will come to the first law of thermodynamics. So thanks for watching, stay tuned.